Late 1937. A small office inside the Rolls-Royce factory in Derby. On one side of the desk sat Ernest Hives, the man who ran the most advanced aero engine company in Britain. On the other sat a 30-year-old mathematician who had never touched an aircraft engine in his life. Hives picked up a stack of academic papers from his desk. He flicked through them slowly. Equations, diagrams, theoretical models of airflow. Then he looked up and asked a simple question. What exactly is a Kármán vortex street? The young man tried to explain. He talked about fluid dynamics, about oscillating patterns in airflow, about the mathematics of turbulence. Hives listened. Then he leaned back in his chair and delivered his verdict. You are not much of an engineer, are you? It was not a question. It was a statement of fact, and technically, it was true. The man sitting across from him had a doctorate from Oxford in pure mathematics. He had studied aerodynamics at Imperial College. He had spent years at the Admiralty Research Laboratories, but he had never designed anything, never built anything, never gotten his hands dirty with oil and metal and the brutal reality of pistons firing 50 times per second. And yet, 4 years later, this same man would double the power output of the Rolls-Royce Merlin engine. He would solve a problem that threatened to hand air superiority to the Luftwaffe. He would transform the Spitfire from an outclassed fighter into the most feared interceptor in the European sky. His name was Stanley Hooker, and the insult he received that day in Derby would eventually become the title of his autobiography. Not much of an engineer. So who was this mathematician with no practical experience? And why did Rolls-Royce decide to hire him anyway? Stanley George Hooker was born on the 30th of September, 1907, in Sheerness, on the Isle of Sheppey, in Kent. His father was a clerk. His childhood was ordinary. Nothing in his early years suggested that he would one day reshape the future of British aviation. But Hooker had a gift. He could see patterns in numbers that others missed. Mathematics came to him the way music comes to a composer, not as a struggle, but as a language he already understood. He won a scholarship to Imperial College London, where he studied mathematics. Then he moved to Oxford, to Brasenose College, where he earned his doctorate in aerodynamics in 1935. His thesis explored the behavior of air flowing over curved surfaces. It was elegant, it was theoretical, and it had absolutely nothing to do with engines. After Oxford, Hooker took a position at the Admiralty Research Laboratories in Teddington. He spent his days calculating, modeling, publishing papers on fluid dynamics that perhaps 200 people in the world could fully understand. He was, by every measure, a pure academic, a man of equations and wind tunnels, the kind of person who thought in Greek symbols and differential calculus, the last person you would expect to find on the factory floor of an engine plant. And yet, in January 1938, Stanley Hooker walked through the gates of the Rolls-Royce works in Derby as a newly hired employee. His welcome was underwhelming. He was shown to a small office, roughly 8 feet by 8 feet. Inside there was a desk, a telephone, an empty bookshelf, and nothing else. No instructions, no assignments, no colleagues stopping by to explain what he was supposed to do. For the first few days, Hooker simply sat there. He read the Times. He waited. Nobody came. The company had hired a brilliant mathematician and then, it seemed, had forgotten he existed. Eventually, he gathered his courage. He left his tiny office and wandered into the surrounding workspaces. There, he found rows of young men hunched over drawing boards, sketching engine components with precision and care. They were the draftsmen, the real engineers, the men who turned ideas into metal. Hooker watched them work. He did not yet know their language. He could not read a technical drawing the way they could. But he understood something they did not. He understood the mathematics of air. And that knowledge was about to become very valuable indeed. Because across the English Channel, Adolf Hitler was rearming Germany at a pace that alarmed every strategist in Whitehall. War was no longer a question of if, it was a question of when. And when it came, Britain would have only one high-performance aircraft engine ready for the fight: the Rolls-Royce Merlin. To understand what Hooker walked into, you need to understand what the Merlin meant to Britain in 1938. It was not simply an engine, it was the engine. The only British power plant capable of driving a modern, high-speed fighter aircraft. Everything the Royal Air Force was counting on, every plan, every strategy, every hope of defending the skies over Britain, depended on this single piece of machinery. The Supermarine Spitfire, the Hawker Hurricane. These were the aircraft that would soon become legends. But without the Merlin, they were nothing more than elegant gliders. The airframe was the body, the Merlin was the heart. And what a heart it was! 12 cylinders arranged in a V formation, 27 liters of displacement, over 1,000 horsepower at full throttle. 11,000 individual components, machined to tolerances so fine that a human hair would be considered rough by comparison. When running at maximum power, the pistons inside accelerated from 0 to 60 miles per hour and back to 0 again 50 times every single second. This was not crude machinery. This was mechanical poetry. The man responsible for keeping this poetry running was Ernest Hives. By 1938, Hives was effectively in charge of the entire Rolls-Royce aero engine operation. He had started as an apprentice and worked his way up through sheer force of competence and will. He was blunt, practical, and utterly uninterested in excuses. Hives had a saying that defined the culture at Rolls-Royce: "If the engineers are wrong, then we are all wrong." He meant it. He trusted his technical people completely. And when the Air Ministry made demands, Hives made sure his engineers delivered. Working directly under Hives was a man named Cyril Lovesey. If Hives was the general, Lovesey was the sergeant major. He ran the Merlin development program with an iron grip and an obsession with detail. Lovesey was a pragmatist. He believed you could not truly understand an engine until you had broken it. You had to run it until something failed. Only then did you know where the real limits were. When Hooker arrived at Derby, he was assigned to share an office with Lovesey. It was an odd pairing. Lovesey, the hands-on mechanical man who thought in terms of metal and stress and heat. Hooker, the theoretical mathematician who thought in terms of equations and airflow and pressure gradients. They could not have been more different. And yet, this partnership would prove to be one of the most productive in the history of British engineering. But in 1938, none of that mattered yet. What mattered was that Britain was running out of time. Germany was building aircraft at an alarming rate. The Luftwaffe was growing stronger every month. And the Merlin, for all its brilliance, had a problem. A problem that the best engineers at Rolls-Royce had been struggling with for years. A problem rooted in the basic physics of how air behaves at high altitude. The Merlin could dominate the sky at 10,000 feet, but above 20,000 feet, it began to choke. And the war that was coming would not be fought at 10,000 feet. To understand the Merlin's problem, you first need to understand how a piston engine breathes. An internal combustion engine is, at its core, an air pump. It sucks in air, mixes it with fuel, compresses the mixture, and ignites it. The more air you can force into the cylinders, the bigger the explosion, and the more power you produce. On the ground, at sea level, there is plenty of air. The atmosphere pushes down with 14 pounds of pressure per square inch. The engine breathes easily. But climb to 30,000 feet and everything changes. At that altitude, the air pressure drops to less than 1/3 of what it is at sea level. The air becomes thin, sparse. There is simply not enough oxygen to feed the engine properly. A Merlin that roars with over 1,000 horsepower at low altitude becomes sluggish and weak in the stratosphere. It gasps, it struggles, it suffocates. The solution to this problem had been known for decades. It was called a supercharger. Think of it as a mechanical lung, a device that forces more air into the engine than it could breathe on its own. The Merlin's supercharger was a centrifugal compressor. At its heart was a spinning disc called an impeller, roughly 10 inches in diameter, rotating at enormous speed. Air entered the center of this disc and was flung outward by centrifugal force, compressed, and then fed into the engine's cylinders. At low and medium altitudes, it worked beautifully. The supercharger kept the Merlin breathing strong, delivering consistent power up to around 16 or 18,000 feet. But above that altitude, even the supercharger began to struggle. The impeller could only spin so fast. The air was simply too thin for a single stage of compression to make up the difference. By 30,000 feet, power output dropped dramatically. The Spitfire, so nimble and deadly at lower altitudes, became slow and unresponsive near the edge of the stratosphere. And this was a serious tactical problem, because warfare was moving upward. Bombers flew high to avoid anti-aircraft fire. Fighters needed to climb even higher to intercept them. The nation that controlled the high altitude would control the sky. And in 1938, the Merlin could not compete in that arena. The engineers at Rolls-Royce understood this. They had been working on supercharger improvements for years. They experimented with different impeller shapes. They adjusted gear ratios. They tested new materials. It was meticulous, grinding work, driven by intuition and trial and error. Small gains here, marginal improvements there. But nobody had approached the problem mathematically. Nobody had sat down with the fundamental equations of fluid dynamics and asked a simple question. What is actually happening to the air inside this machine? Nobody, that is, until a young mathematician with no engineering experience wandered out of his empty office and asked if he could take a look at the supercharger drawings. What Stanley Hooker saw in those drawings would change everything. When Hooker finally got his hands on the supercharger drawings, he did not see what the other engineers saw. They saw a proven design, a reliable component that had been refined over years of development, a machine that worked. Hooker saw something else entirely. He saw inefficiency hiding in plain sight. The air intake that fed the supercharger was cramped, squashed. The airflow had to make a sharp 90-degree turn before entering the impeller, forcing itself through 6 separate openings that disrupted the smooth passage of air. To a practical engineer, this was simply how it was done. To a mathematician trained in fluid dynamics, it was a disaster. Hooker understood something fundamental. Air does not like to be forced around corners. Every sharp turn creates turbulence. Every disruption wastes energy. And wasted energy means lost power. The supercharger was fighting against its own design before it even began compressing the air. He started calculating. Using the same mathematical tools he had developed during his years at Oxford and the Admiralty, he analyzed the airflow through every section of the supercharger. He measured angles. He computed pressure losses. He mapped exactly where the inefficiencies were hiding. Then he proposed a radical redesign. Instead of the cramped side entry intake, Hooker designed a smooth central entry system. Air would flow directly into the center of the impeller without sharp turns or obstructions. He recalculated the angles of the guide vanes that directed air onto the spinning disc. He reshaped the diffuser that slowed the compressed air before it entered the engine. The new intake created a distinctive bulge at the rear of the engine housing. The factory workers, with typical British irreverence, nicknamed it the baby's bum. The name stuck. But what mattered was not the shape. What mattered was what the numbers showed. The original supercharger operated at roughly 65% efficiency. That meant 35% of the energy used to spin the impeller was being wasted, lost to turbulence and friction and poor airflow. Hooker's redesigned supercharger pushed efficiency up to 76%. 11 percentage points may not sound dramatic, but in the world of engine performance, it was transformational. The improvement translated directly into power. Production Merlins fitted with Hooker's new supercharger design delivered approximately 30% more horsepower than their predecessors. 30%. Not from a new engine, not from exotic materials or revolutionary technology. From mathematics. From understanding the invisible behavior of air. The skeptics at Rolls-Royce went quiet. The man who was not much of an engineer had just achieved something their years of trial and error had failed to deliver. His methods were unconventional, his background was unusual, but his results were undeniable. By 1941, Stanley Hooker was no longer the awkward outsider reading the Times in an empty office. He was the head of supercharger development, one of the most critical roles in the entire company. Ernest Hives, the man who had doubted him, now trusted him completely. The Merlin was stronger than ever. The Spitfire was faster than ever. Britain had survived the Battle of Britain, and the RAF controlled its own skies. And then, in the summer of 1941, something appeared over the coast of France. Something the British pilots had never seen before. A fighter so fast, so agile, and so deadly that it threatened to undo everything Hooker and his team had achieved. The Luftwaffe had a new weapon, and the Spitfire was suddenly outclassed. Summer 1941. The skies over northern France. RAF fighter pilots on routine patrols began reporting something strange. They were encountering German fighters they did not recognize. Radial-engined aircraft, compact and aggressive, with a silhouette that matched nothing in their identification manuals. At first, intelligence officers dismissed the reports. The aircraft were probably captured French machines. Curtiss Hawks, seized after the fall of France and pressed into Luftwaffe service. Unusual, but not alarming. Then the combat reports started coming in, and they told a very different story. These unknown fighters were fast, brutally fast. They climbed like nothing the RAF had ever faced. They rolled into turns with a speed and precision that left Spitfire pilots struggling to follow. And when they dove away, they simply vanished, accelerating beyond any hope of pursuit. This was no obsolete French design. This was something new, something dangerous. The aircraft was the Focke-Wulf 190. The Germans called it the Würger, the butcher bird, after a small predatory shrike that impales its prey on thorns. The name was fitting. When British intelligence finally captured an intact specimen in June 1942, they tested it against the Spitfire Mark V, the RAF's frontline fighter. The results were devastating. At 2,000 feet, the Focke-Wulf was 25 to 30 miles per hour faster than the Spitfire. At 3,000 feet, the gap widened to 35 miles per hour. Its roll rate was the highest of any fighter aircraft in the entire war, allowing German pilots to flick into evasive maneuvers that British pilots could not match. Its climb rate exceeded the Spitfire at almost every altitude. The Spitfire had exactly one advantage. It could turn in a tighter circle. That was all. For a fighter pilot, these numbers were not abstractions. They were the difference between coming home and not coming home. Johnny Johnson, who would become the highest-scoring RAF ace against the Luftwaffe, later described what it was like to face the Focke-Wulf in those early days. The German fighters, he said, drove them back to the coast. The RAF, which had won the Battle of Britain less than a year earlier, was now struggling to maintain any presence over occupied France. By November 1941, the situation had become critical. RAF Fighter Command was forced to halt most daylight operations over the continent. The losses were simply too heavy. When operations resumed in the spring of 1942, the results were no better. Squadron after squadron came back with fewer aircraft than they had sent out. Britain needed an answer, a new fighter that could match the Focke-Wulf at every altitude and in every maneuver. But designing a new aircraft from scratch would take years. New airframes required new factories, new tooling, new supply chains. The RAF did not have years, it barely had months. There was only one possibility, one desperate option that might close the gap before it was too late. They could not build a new aeroplane, but perhaps they could transform the one they already had. Perhaps they could take the Merlin engine and force it to deliver power it was never designed to produce. The Air Ministry turned to Rolls-Royce with a demand that bordered on the impossible. They needed a Merlin that could fight at 40,000 feet, and they needed it now. The request from the Air Ministry arrived at Rolls-Royce with the weight of desperation behind it. Britain needed a Merlin engine capable of delivering full combat power at 40,000 feet. Not adequate power, not acceptable power, full power. The kind of power that could chase down a Focke-Wulf in the thin, frozen air at the edge of the stratosphere. On paper, the solution seemed obvious. If one supercharger could not compress the thin, high-altitude air sufficiently, then use two. A two-stage system. The first impeller would compress the air partially, then feed it into a second impeller for additional compression. Twice the squeezing, twice the pressure. Problem solved. Except physics does not negotiate. When you compress air, you do not simply make it denser, you also make it hotter. This is not a flaw in the design, it is a fundamental law of thermodynamics. Compression generates heat. There is no way around it. A single-stage supercharger already raised the temperature of the intake air significantly. Adding a second stage of compression pushed that temperature to dangerous levels. By the time the air passed through both impellers, it had reached approximately 200 degrees Celsius, 400 degrees Fahrenheit. At that temperature, the fuel-air mixture does not wait for the spark plug. It ignites spontaneously the moment it enters the cylinder. This is called pre-ignition, and it is catastrophic. Instead of a controlled burn pushing the piston downward, you get an uncontrolled explosion that hammers the piston from the wrong direction. The forces involved are enormous. Pistons crack, connecting rods bend, bearings melt. An engine designed to produce power instead tears itself apart from the inside. The engineers at Rolls-Royce understood this problem intimately. They had tested two-stage configurations. They had watched engines fail on the test stands. The physics was clear. You could have the pressure, or you could have a working engine. You could not have both. Across the Atlantic, American engineers had found a different path. Instead of gear-driven superchargers, they used turbochargers, devices powered by exhaust gases rather than the engine's crankshaft. The Lockheed P-38 Lightning and the Republic P-47 Thunderbolt both used this approach to achieve excellent high-altitude performance. But turbocharging came with its own costs. The system required extensive ducting to route exhaust gases to the turbine and compressed air back to the engine. It needed intercoolers, wastegates, and complex control systems. The P-47, built around its massive turbocharger installation, was one of the largest and heaviest single-engine fighters of the war. The Spitfire was a different philosophy entirely. It was small, it was light, it was designed around the compact elegance of the Merlin engine. There was simply no room in that slender fuselage for the bulky plumbing that turbocharging required. Redesigning the airframe to accommodate such a system would take years and produce an entirely different aircraft. Years that Britain did not have. So the challenge remained. Rolls-Royce needed to build a two-stage supercharger that could deliver the pressure without delivering the heat. A system that could compress the air twice while somehow keeping it cool enough to burn safely. Every instinct said it could not be done. The thermodynamics were against them. The timeline was impossible. The Spitfire's compact design left almost no margin for additional equipment. And yet, Stanley Hooker believed he had found an answer. A solution so elegant, so mechanically audacious, that no other manufacturer in the world would successfully implement it during the entire war. He was not going to fight the heat. He was going to remove it. The problem was heat. 200 degrees Celsius of it, turning perfectly good intake air into a weapon that would destroy the engine from within. Every engineer at Rolls-Royce understood the challenge. The question was, how to solve it without adding weight, complexity, or bulk that the Spitfire simply could not accommodate. The conventional answer was an air-to-air intercooler, a heat exchanger similar to a car radiator placed between the two supercharger stages. Hot compressed air would pass through a matrix of thin tubes while outside air flowed over them, carrying the heat away. American turbocharger installations used exactly this approach, but the Spitfire was not an American heavy fighter with room to spare. An air-to-air intercooler large enough to handle the heat output of a two-stage Merlin would require substantial ducting. Air scoops, internal channels. The most practical location would be directly in front of the cockpit, exactly where the pilot needed to see. Blocking the forward view of a fighter pilot was not an acceptable compromise. Hooker approached the problem differently. If he could not use outside air to cool the intake charge, he would use something else, something already present in the aircraft, something that could absorb enormous amounts of heat without requiring massive external ducting. Liquid coolant. The Merlin was already a liquid-cooled engine. A mixture of water and ethylene glycol circulated through passages in the cylinder block, absorbing heat from combustion and carrying it to radiators mounted under the wings. This system was proven, reliable, and already integrated into the Spitfire's design. Hooker's insight was deceptively simple. He would create a second independent cooling circuit dedicated entirely to the intercooler. Hot, compressed air leaving the first supercharger stage would pass through a heat exchanger built directly into the supercharger housing itself. Coolant would flow through passages cast into the metal, absorbing the heat and carrying it away to a small dedicated radiator mounted in the starboard wing. It was, in engineering terms, a plumbing nightmare. The system required its own water pump, its own header tank, its own radiator, its own network of hoses and connections. It added weight. It added complexity. It added dozens of potential failure points. But it worked. The intercooler dropped the temperature of the compressed intake air from 200 degrees Celsius to approximately 60 degrees. 140 degrees of potentially destructive heat simply carried away by circulating liquid. The air entering the engine cylinders was now dense, cool, and stable. No pre-ignition, no detonation, no melting pistons. What made Hooker's solution remarkable was not just that it worked, it was that nobody else managed to replicate it. The Americans had their turbochargers, the Germans had their own supercharger designs, but a compact, liquid-cooled intercooler integrated directly into a two-stage gear-driven supercharger fitted into a small single-engine fighter, this was unique. No other nation fielded anything comparable during the entire war. The engine that emerged from this work was designated the Merlin 61. It was the same basic architecture that had powered the Spitfire since 1938. The same 12 cylinders, the same fundamental design. But with Hooker's two-stage supercharger and intercooler, it was transformed. At 30,000 feet, where the original Merlin produced barely 500 horsepower, the Merlin 61 delivered over 1,000. A full doubling of high-altitude power. The invisible ceiling that had constrained the Spitfire for years had been shattered. Now came the harder part. Turning a prototype into a production engine, fitting it into an existing airframe, training ground crews to maintain a system far more complex than anything they had worked on before, and doing all of it fast enough to matter, because every week that passed, more RAF pilots climbed into their outclassed Spitfire 5s and flew out over the channel. Some of them did not return. The solution existed. The race now was to deliver it before the cost became unbearable. Development moved at a pace that would have been unthinkable in peacetime. In March 1941, the first experimental 60 Series Merlin roared to life on a test stand at Derby. 4 months later, in July, the engine flew for the first time, mounted in a modified Spitfire airframe. The results exceeded expectations. The aircraft climbed faster, flew higher, and performed better than anything the RAF had ever fielded. But engines on test stands do not win battles. Aircraft in prototype form do not protect convoys or escort bombers. The gap between a working prototype and a combat-ready squadron was measured in months of manufacturing, testing, and training. Months that the RAF did not have. While Rolls-Royce engineers worked around the clock in Derby, the situation over the English Channel was deteriorating. By November 1941, RAF Fighter Command made a painful decision. Daylight operations over occupied France were suspended. The Focke-Wulf 190 had made the cost too high. Too many pilots were being lost. Too many aircraft were failing to return. For an air force that had won the Battle of Britain just 14 months earlier, it was a humbling reversal. The suspension could not last forever. In the spring of 1942, operations resumed. Fighter sweeps over northern France, escort missions for light bombers attacking coastal targets. The RAF needed to maintain pressure on the German defenses, to tie down Luftwaffe units that might otherwise be sent to the Eastern Front. The results were grim. March, April, May, June. Month after month, the loss rates remained unacceptably heavy. Squadrons equipped with the Spitfire Mark V flew out over the Channel, knowing they were facing an aircraft that could outrun them, outclimb them, and outmaneuver them in almost every situation. Courage was not enough. Skill was not enough. The machinery was simply outmatched. At Rolls-Royce and Supermarine, engineers knew that help was coming. The new Spitfire Mark VII and Mark VIII were being designed specifically around the two-stage Merlin. They would have pressurized cockpits, redesigned fuselages, and strengthened structures to handle the increased performance. They would be everything the RAF needed. But they would not be ready until 1943 at the earliest, a full year away. 12 more months of attrition. 12 more months of pilots climbing into aircraft they knew were inferior. Someone at the Air Ministry, or perhaps at Supermarine, asked an uncomfortable question. Did they really need to wait for a completely new aircraft? The Merlin 61 existed. It worked. Could they simply install it in the airframe they already had? The Spitfire Mark V was in full production. Factories understood it. Ground crews knew how to maintain it. Pilots were trained on it. If the new engine could be fitted into the existing airframe with minimal modifications, aircraft could reach the squadrons in months rather than years. It was not an elegant solution. The Mark V airframe had never been designed for an engine this powerful. The installation would require modifications to the engine mounts, the cooling system, and the cowling. It would be a compromise, a stopgap, an improvisation born of desperation. But it could be done quickly, and quickly was all that mattered. The aircraft that emerged from this forced marriage was designated the Spitfire Mark IX. It was not a new design. It was not a carefully optimized system. It was a proven airframe with a revolutionary engine bolted into it, sent into combat because waiting for perfection would cost too many lives. In July 1942, the first production Spitfire Mark IXs arrived at RAF Hornchurch, home of No. 64 Squadron. The pilots who received them had spent months fighting at a disadvantage. They had learned to fear the Focke-Wulf. They had buried friends who had fallen to its guns. Now, for the first time, they had an aircraft that could fight back on equal terms. On the 28th of July 1942, the Spitfire Mark IX flew its first operational mission. The skies over France were about to change. The 28th of July 1942. A warm summer morning at RAF Hornchurch, east of London. The pilots of No. 64 Squadron walked to their aircraft for a mission they had flown dozens of times before. A fighter sweep over the French coast. Rodeo operations, the RAF called them, show the flag, draw up the enemy, fight if necessary. But this mission was different. For the first time, they were not climbing into the familiar cockpits of the Spitfire Mark V. They were strapping into something new, something that promised to change everything. From the outside, the Spitfire Mark IX looked almost identical to its predecessor. The same elegant, elliptical wings, the same graceful curves. Only small details hinted at the transformation within. Slightly longer engine cowlings, additional air intakes, a subtle difference in the exhaust stubs. But the moment the pilots pushed the throttle forward, they understood. This was not the same aircraft. The acceleration pressed them back into their seats with an authority the Mark V had never possessed. The climb rate was extraordinary. The engine pulled them skyward with a smoothness and power that felt almost effortless. 2 days later, on the 30th of July, the Spitfire Mark IX claimed its first confirmed victory. A Focke-Wulf 190, the aircraft that had terrorized the RAF for over a year, fell from the sky over France. The hunters had become the hunted. The performance comparisons told the story in cold, precise detail. At 8,000 feet, the Spitfire Mark IX was 8 miles per hour faster than the Focke-Wulf. At 15,000 feet, the advantage grew to 5 miles per hour. Above 25,000 feet, the gap widened dramatically. The two-stage Merlin came into its own exactly where the single-stage engine had always struggled. Maximum speed, 409 miles per hour at 28,000 feet. The Mark V had managed 369, 40 miles per hour faster. In aerial combat, where engagements were decided in seconds, 40 miles per hour was the difference between catching your enemy and watching him escape. Wing Commander Alan Deere, one of the most experienced fighter pilots in the RAF, flew the new Spitfire and delivered his assessment. At 21,000 feet, he reported, the Mark IX was approximately 30 miles per hour faster than the Focke-Wulf. It was better in the climb, and it was vastly more maneuverable. Vastly more maneuverable. From a pilot who had been fighting since 1939, who had survived Dunkirk and the Battle of Britain, those words carried weight. Johnny Johnson, who would finish the war as the highest-scoring RAF ace against the Luftwaffe, later reflected on what the Mark IX meant to the pilots who flew it. Fighter pilots of every nationality, he said, thought the Spitfire 9 was the best close-in fighter of them all. Not the fastest, not the highest flying, not the most heavily armed, the best close-in fighter. The aircraft you wanted when the battle came down to skill against skill, nerve against nerve, in the swirling chaos of a dogfight. The aircraft that responded to your hands like an extension of your own body. The Spitfire Mark IX would go on to equip more squadrons than any other variant in the aircraft's long history. It fought over North Africa, over Sicily and Italy, over the beaches of Normandy on the 6th of June 1944. It remained in frontline service until the final days of the war in Europe. A stopgap, an improvisation, a desperate compromise born from necessity, and yet it became legendary. But Stanley Hooker was not finished. The Merlin 61 had answered the immediate crisis, but the war was far from over. The Luftwaffe would not stand still. They would improve their own aircraft. They would find new ways to challenge Allied air superiority. Hooker understood that engineering was not a destination. It was a race. And as long as the war continued, he intended to keep running. The Merlin 61 had solved the crisis. The Spitfire Mark IX had restored balance in the skies over Europe. A lesser team might have considered the job done. Hooker and his colleagues saw it differently. The enemy would adapt. The moment you stopped pushing forward was the moment you began falling behind. The war was evolving. High-altitude interception remained important, but the RAF was increasingly called upon to operate at lower levels. Ground attack, close air support, and, most urgently, hunting V-1 flying bombs streaking toward London below 5,000 feet. The two-stage Merlin excelled in the stratosphere, but at low altitude, its capability was being wasted. The supercharger, sized for 30,000 feet, forced too much air into the engine at sea level. Pilots had to throttle back, leaving power on the table. Hooker's solution was elegant. He reduced the impeller diameter slightly. The engineers called it cropping. A cropped supercharger sacrificed high-altitude performance, but at low altitude, the engine could run at full throttle. The Merlin 66 became the heart of low-altitude Spitfires that hunted flying bombs in the desperate summer of 1944. But the most dramatic gains came from chemistry. In May 1944, weeks before Normandy, 150-grade fuel reached frontline squadrons. With this fuel, the Merlin 66 produced 2,000 horsepower, twice what the engine delivered in 1939. Same cylinder block, same architecture, twice the power. On test stands at Derby, Hooker's team pushed further. An experimental engine, RM-17SM, running on 150 octane with water methanol injection, produced 2,640 horsepower. Never intended for production, a demonstration of what was possible when engineers refused to accept limits. By May 1945, the Merlin had doubled its output. A young mathematician who had sat alone reading the Times in 1938 had helped create the engines that swept the Luftwaffe from European skies. Ernest Hives had been right, in a sense. Stanley Hooker was not much of an engineer, not in the traditional meaning. He was something else entirely. In 1984, Stanley Hooker published his autobiography. He was 77 years old. He had been knighted. He had shaped jet engines that powered aircraft from the Hawker Hunter to the Harrier. He had saved Rolls-Royce from collapse more than once. He could have chosen any title. Instead, he chose 5 words that Ernest Hives had spoken to him in Derby, nearly half a century earlier. Not much of an engineer. It was not bitterness, it was a statement. Hives had been technically correct, and that correctness had missed the point entirely. At Rolls-Royce, there were design men who created blueprints, and development men who made those designs work through testing. Hooker was neither. He came from theoretical mathematics, a world most practical engineers viewed with suspicion. Yet he transformed everything he touched. He brought equations where intuition had ruled. He could see invisible rivers of air flowing through machinery and identify problems that experienced engineers had walked past for years. Decades later, test pilot Bill Bedford was asked who was Britain's greatest engineer. His answer was clear. If asked, he said, "I would have to decide between Brunel and Sir Stanley Hooker, but I would probably go for Sir Stanley." So was Hives wrong? Perhaps. Or perhaps he was exactly right. Hooker was never an engineer in the traditional sense. He was something new. A mathematician who wandered into a world of metal and oil and quietly revolutionized it. Not much of an engineer, no. He was something better.